Yeah, so I won't repeat the joke of Lucilla and Mathilde, but now we are actually back at that slide from this morning. So you might remember that at the beginning we mentioned something with deeper and wider, and now we're actually coming from the deep, really detailed measurements and, let's say, findings to a wider approach. So we're taking now a view into our greenhouse for the ones who were not able to see it yesterday, and describe our new setup after we dismantled all the pots for our measurements and samples here. So actually, what have we done? There are still buckets on buckets. So the principal setup looks the same. But we've changed a few things. Like minor changes were that we adjusted the holes between the bottom of the soil bucket and the holes in the lid of the leachate collection tank to just guarantee that we don't have any, let's say, mechanical cloggings in between the buckets. That's a smaller change. But also mentioned yesterday, we adjusted the vegetation with this new experiment to a mix of 2 grasses and a microclover to be sure in a larger scale with different, let's say, soil properties that we actually have vegetation. Because from the past we figured out if we're growing just one grass type and it's not that good performing on the soil, then the reseeding and getting the dead grass removed interacts more and affects more the leachate alkalinity and leachate measurements than actually having sometimes some seeds from the air going inside and creating other plants in the buckets. We try to avoid that, but it's still 550 buckets. And the last biggest change we now have is we don't have replicates for everything anymore. We just have 3 replicates for the controls and 1 bucket for each treatment. Why is that? So with the past results, we could actually see that if we do some statistics, that 78% of all of our results between control and treatment, we could figure out with 1 replicate. That's good, but there's still a lack of where it doesn't fit. The good thing is it was not affecting, let's say, something where we recognized we create higher results with only having 1 replicate. We actually just recognized we are not clear in the, are we in the range of the control or below? So right now with this approach, we don't want to look into one specific soil feedstock combination to get an idea this specific combination is giving you X tons of CO2 per year, but we want to understand how the different rock properties and soil properties are interacting. So we want to use like an approach, which we'll come to in this presentation, to understand how the different properties are pushing the system towards more leachate alkalinity or less. Now, just to give you a rough idea, if we build up 600 buckets with 3 controls for the control, 3 replicates for the control, to be sure that the control value is right, because we compare the treatments to the control, with just 1 replicate, we end up with the, let's say, path A, with way more soils and way more combinations, where if we build up 3 reps also for the treatments, we end up with less. And we have, let's say, human capacity which is limited, and also room capacity which is limited in a greenhouse. So how did we actually select now the feedstocks and the soils we picked for the new experiment? So my colleague Ingrid had this nice idea that we're looking at the dissolution kinetics of the different minerals, and we try to cover actually some really fast weathering and dissolving minerals with some really slow ones. And we want to cover just the entire area. Now, for that, we looked at XRD, XF measurements, and we came to an overview, or let's say a categorization, that we could put some different minerals into categories. Now, the categories come into play right now. We have a core experiment where we have our 3 controls, And then we have a feedstock with magnesium silicate, a carbonate feedstock. We have one which is representing basalt, another one with just calcium magnesium silicate, a glacial felsic, another basalt. We have undersaturated and oversaturated, or saturated. It's just saturated, thanks. And we have a mixture where we combined the carbonate material with the ultramafic magnesium silicate to see if there are some other interactions. All of that was milled so that we can at least compare it a little bit better from milled and unmilled feedstocks. We can't guarantee that they all have the same particle size distribution, but we looked for going below 70 micrometers for the biggest grains. And we applied to every pot 40 tons per hectare to compare it. Now, this is not the only part of the experiment. This is just the core. Every soil we added gets at least the 10 buckets of the core experiment. A few soils, which are presenting then a certain area for soil properties, we're coming to that next, got even more, so the extended version. So it's like a subscription model here, so that's a basic one at the top, then there's the more advanced in the middle, which is presenting other feedstocks of that specific category. So we have another carbonate material, for example. We have another basalt, another calcium magnesium silicate, and so on and so on. The premium version of the subscription in the end is the milled versus original comparison. So that we in the end have 23 pots where we have specific materials which are milled before and compared to the unmilled one. Now, to connect this later for machine learning or for any kind of model, we need a bridge experiment because we have now another vegetation on it. So we built up on one specific soil, again, Lufa 2.2, but it's batch C now. Feedstocks from our previous experiment with the new plant and the old plant, and the same with the current used feedstocks, with the old and new plant, to be sure that we can compare things. Now, coming from the feedstock to the soil. Now, we had actually pretty luck with getting different soils. We had nice interactions with different contributors and different organizations. And what you see here is just the overview of our used soils on the pH scale. So you can see from the very top that we have a really acidic soil with 3.3, 4, until at the very bottom a soil with a pH of 7.5. The 3.3 and especially the ones at the very top are not normal agricultural field soils. They're, let's say, the ones we try to get an upper or really like an extreme for the pH. It's not the common soil from agricultural fields. Now, to show you a little bit what else is describing soils is the CEC range, where we have a soil with CEC, the soil number 21, with 1.1 till 25.4, which is also partly connected to how much silt and sand you have in these soils. Last but not least, the TOC and TIC is also varying. The TIC is, let's say, not that showing of a big range, but as you all know, a TIC present in the soil can also cover our alkalinity signal by just weathering the soil and the carbonates in there, especially if you add so much irrigation water as we do. But the TOC is changing. Of course, there are soils in Germany and all over the world with way more organic carbon, but this is at least the scale we have because we focused on pH and CEC. Now, this is just an overview to show you how the different rocks and feedstocks are distributed before we now come to the actual first results. People who have visited the EGU in Vienna already know the slide, so I'm sorry for that. It's the same one. But what you can see, as we also described this morning, is that you see a general trend of how fast a certain mineral, or let's say a rock, is weathering. At the lower bottom for the ones back there, I will just describe it roughly. You can see the mouse. So the first three columns are actually a calcium magnesium silicate. Then we have an industrial material. If you have questions to those materials, we can clarify that later. Then we have a calcium silicate, our mixture of carbonates and the magnesium silicate. Carbonates over here. Then we have a magnesium silicate, different basalts until here. And then we have here some glacial felsic material. Now, of course, we can look at the far left of this figure, where we have the total accumulated alkalinity in leachate over time, which is, if you look at the color coding here, pretty promising in comparison to the far right, where we have more, let's say, the same values at the moment as the control or lower. But you also see within the feedstocks, above all the different soils, I should mention that. So here's the pH of the soil and the CC, so every row is on a different soil. You can see that the different soils are still making a huge difference if you want to apply a certain feedstock somewhere. So you can be lucky, or you can have the case where we just used our basalt on the third soil and have seen basically the same signal as the control. Now, like I mentioned, the experiment is actually bigger, so this was just a subset. If you look at the entire unmilled and the bridge experiment, this would expand even more. But yeah, to keep it a little bit easy to understand, I should have chosen the one before. Now, what are we actually doing with this data? So I mentioned model before, but so we somehow need to use our, let's say, chance to have this variation in feedstocks and soils to understand maybe drivers for certain parameters. Now, we have already soil features initially measured. We have also still samples of the initial soil to measure maybe some things we heard today. For the model, we have our feedstock features already measured. What will be something in the future after we harvested the buckets again will be the soil features after the experiment. We will have our resulted leachate alkalinity, at least to train a model on how much alkalinity was created. We can also train it in different directions. If, for example, we have a method which is usable for our greenhouse setup for organic carbon stabilization, then we could also use that as an initial and then post a result. But what are we doing with it? So I'm very happy that my boss and CEO is really happy about using AI and models and calculations. So we already have some preliminary data about what Dirk has in the last days worked on. So he compared 20 different models, and at least with our preliminary leachate results, there's a really nice approach with a random forest model, which you can see here. So I just try to explain it as short as possible because I have less than 2 minutes left. But there is actually a model looking at our soil and rock data, which is the gray graph. I'm just describing the colors first. And it uses, let's say, it learned with all of our leachate results, and then it just takes the rock and soil features and models 50% the accumulated alkalinity over time in a range of plus minus 20% failure. So if you would look at the accumulated graph, then we are fitting with just the initial soil and feedstock in the range that 50% fit in the 20% area, error area. Now, if we just add the EC and volume and take out the soil and feedstock values, so we just look at volume and EC over time, we can even predict the outcome of the actual measurement of 69% or 68% of the results. The more data we add, now in the black one here with lab and plus EC and volume, the closer we're getting to actually a real result, which we measured by looking at TA and DIC, and which is really promising, at least for us in the greenhouse. We won't change it for the machine learning, but for future experiments. If we look on 1 year of sampling, we could just take our rock and soil features, add the EC and volume over every measurement event, and use 2 titration tests on the entire year to nearly fit the same as measured, which is, I think, really promising and cool. I hope you just read what the difference between LOCO and LSRO are. I can explain it very short here. So these are all the cells we actually measured. So if we're modeling something with LOCO, which is leaving one cell out, it will leave one cell here out from the results. If there is this LSRO, so leaving one row out, soil rock out, leaving the soil rock out, then it has to model the whole row for the soil rock combination, and it still gets promising results. Now, this is future music, and it's of course not like fully right, but if we already can have such good chances in modeling our real measurements, then something like this could soon look like this, that we get at least an area of an idea where a certain feedstock and soil combination would end at. And with that, let's say, results, I just hope that we can also do this later with maybe other measurements in just soil to use it outside. But yeah, that's future music. Now, my time is over. I just need to get my phone because I wanted to mention all the names at least who were contributing at the beginning. My phone is in my bag, so I'm sorry. Because I don't want to miss anybody. Wait. Okay.
Then you have to forget someone.
I will just do my best. So, of course, we're thanking all the collaborators who are here today, who worked on projects. I want to thank everybody who was there when we built up the initial trial which led to the soil samples here. From Mathilde to Elena to Lukas to Xuming to Jens Hartmann to Jelle to Johannes Barth to Philipp Pogge to, of course, our team, to Anna Pessler, to Moni, who also helped at that day, to Johannes Meyer-Zudrewer, to Nico Hagemann, Ralf, Torben Ammann, and I really enjoy seeing all of you communicating in the breaks, and I hope to have tomorrow a really good communication and interaction in the sessions. And of course, Patrick Niedermeyer and Jörn Pessler. And that's it. Okay. So thank you everybody for all of your work, for all of your eager to work on this, and hopefully we can achieve something more promising in the future, or yeah, that's it.